Let's take a look at the differential amplifier. First of all, we know that Vp is equal to Vn. That is, the voltage entering the positive terminal is equal to the voltage entering the negative terminal. With that information, we know that Vb is also equal to Vp. Therefore, Vb is equal to Vn, which is equal to Vb. Next, using nodal analysis, we can find out what V out is going to be. So we'll take VB minus VA divided by our resistance, which is 25K, plus VB minus V out divided by 100K. And this is going to be equal to 0. Solving for this, we're going to have 125K VB minus 100 VA is equal to 25 V out. And plugging in, you're going to end up with V out is equal to negative 3 volts. Another way to look at this is superposition. So say we take VB and we deactivate it, so the voltage there is at 0. So going with the formula, we're going to have 0 minus VA, which is 2 volts, divided by 25K, our resistance, plus VB, which is 0, minus V0 over 100K is equal to 0. Solving for this, we will have V0 prime is going to equal negative 8 volts. And now the other side of our superposition, we're going to deactivate VA. So with VA equal to 0, we're going to have VB, which is 1, minus VA, which is 0, over 25K, plus 1 minus V out. We're going to denote that as double prime over 100K is equal to 0. Solving for this, we'll have V naught double prime is going to equal to 5 volts. Finally, V out is going to be equal to V out prime plus V out double prime, which is equal to negative 8 volts plus 5 volts, which is going to equal negative 3 volts, which is the same answer we had before. Based on our knowledge of op amps, we know that in an inverting configuration, V out is equal to negative R2 over R1 times V in, with negative R2 over R1 equal to the gain of our op amp. And we know that in a non-inverting configuration, V out is going to be equal to R2 over R1 plus 1 times V in a non-inverting configuration. So going back to the superposition method, negative R2 over R1 times V in, we're going to have V in being VA, which is going to be equal to 2 volts. So we'll have negative R2 over R1, which is 100K over 25K times V in, which is going to be 2 volts, which is going to equal to negative 8. And then for our non-inverting setup, we're going to have the same thing. So 100K divided by 25K is 4. So we're going to have 4 plus 1 times V in, and our V in this time will just be 1 volt, and we'll have equals 5 times 1 is going to be 5, and 8 plus 5 is going to be negative 3. Therefore, our final equation for V out is going to be equal to negative R2 over R1 times VA plus R2 over R1 plus 1 times VB. So now, using a slightly more complicated setup, we can use our formula from before to easily find what the voltage at the output will be. So we know from the voltage divider that V1, which is equal to 2 volts, we're going to have VP here that we need to solve for. So VP is going to equal V1 times R4 divided by R3 plus R4, which is equal to 2 volts times 4K divided by 4K plus 4K, which is equal to 1/2. So our final voltage is going to be 1 volt. Putting this all together, we're going to have V out is going to equal, first we'll start with the non-inverting side. We'll have 1 plus R2 over R1 times VP plus negative R2 over R1 times VA. Substituting everything in, we're going to have 1 plus 2K over 1K times 1 volt, which we determined before, plus negative 2K over 1K times 3 volts. This comes out to negative 3 volts. There are certain cases when we can simplify this formula for the differential amplifier, and this case is going to be when R1 is equal to R3 and when R2 is equal to R4. So when you're solving, you're going to have V out is going to be equal to R2 over R1 plus 1 times R4 over R3 plus R4 using the voltage divider times V1 plus negative R2 over R1 times VA. Solving this out, you're going to have 2 plus 1 times 4 over 6, which is 2/3, times V1, which is 2, plus negative R2 over R1, which is going to be negative 2, times VA, which is going to be 3, which is equal to negative 2 volts. Doing some arranging, you can come up with the equation that V out is going to equal R2 over R1 times V1 minus VA. Checking this answer, we're going to have 4K over 2K, which is just going to be 2, times V1 minus VA, which is 2 minus 3. We're going to have negative 1 times 2 is equal to negative 2 volts. I encourage you to check this on your own time by writing this out and solving for V1 minus VA. And you can solve for the gain R2 over R1. Another trick when simplifying these is if R1 is equal to R2, which is equal to R3, which is equal to R4, with all four resistors equal. In this configuration, you're going to have V out is going to equal to 1 plus R2 over R1 times R4 over R3 plus R4 times V1 plus negative R2 over R1 times VA. Solving for this, you're going to have 1 plus R2 over R1, which is 4K over 4K, which is just going to be equal to 1, times R4 over R3 plus R4, which is going to be 4 over 8, which is just going to be a half, times V1, which is 2, plus negative R2 over R1, which is going to be 4K over 4K. You're going to have negative 1, times VA, which is 3. Your final answer is going to be negative 1 volts. If you want to simplify this formula, again, on your own time, when all four resistors are equal, it's simply going to be V out equals V1 minus VA, which is equal to 2 volts minus 3 volts, which equals negative 1 volt. This circuit is called a unity gain differential amplifier, and the voltage gain of the amplifier will be exactly 1 or unity. The previous configurations of differential amplifiers amplify the difference between two voltages. It makes this type of operational amplifier circuit a subtractor. This is unlike a summing amplifier, which adds or sums together the input voltages. Well, this sums it up for differential amplifiers. Be sure to check out other videos for the rest of op amps.